Hello everyone, let's go ahead and take a look at the squeeze theorem. And the squeeze theorem says this: if h of x is less than f of x is less than g of x for all x in an open interval contained in a value c, except possibly at c itself, and if the limit as x approaches c of h of x is equal to L, which is also equal to the limit as x approaches c of g of x, then the limit as x approaches c of f of x is going to be L as well. Now, sometimes these theorems can get quite unwieldy because the language can get quite confusing at times. So let's go ahead and put that in a visual representation, and I think you'll see exactly what the squeeze theorem is saying. So here we have the x-axis, the y-axis. We have two functions, h of x and g of x. I'll put in f of x a little bit later. But notice that we say that h of x is indeed greater than g of x for all values of x in an open interval containing value c. So here's our open interval. C is within there. And notice that for all values of x in this open interval, h of x is indeed greater than g of x, except possibly at c itself. Now, the thing that we also have to take a look at is this other condition, which says that the limit as x approaches c of h of x and g of x both approach L. So if I go ahead again and I approach c from both the left and the right, if I take a look at g and I take a look at h, they're all going to be approaching the limiting value of L. Okay, so everything is set here with regards to our conditions. Now the result, which is the limit as x approaches c of f of x equals L, must also be true. So when I go ahead and I take a look at where f of x is, notice that f of x has to be between h of x and g of x. So if I go ahead and take a look at where f of x could be, f of x could be something like that. Now notice that what's happening, and I think now it is very apparent why this is called the squeeze theorem, is that h of x and g of x are both squeezing f of x, so that as x approaches c, f of x also has to assume the limiting value of L. Okay, so that's basically what we have for the squeeze theorem. Now, there could be a question as to except possibly at c itself. What exactly is that part for? Well, the reason for that is because we said that whenever you go ahead and evaluate limits, the value of the function at this particular value of c doesn't even have to exist. For example, if I go ahead and I put a circle there, which means that all those three functions don't actually exist for x is equal to c, but what we know by our understanding of limits is that the limiting value is still L. So that's the reason for this extra clause here, which says except possibly at c itself. So let's go ahead and take a look at the example. The example says, prove that the limit as x approaches 0 of x squared cosine of 1 over x squared is equal to 0 by using the squeeze theorem. Now, the thing is that what we're going to have to do is we're going to have to consider this part right over here as f of x. Okay? So this is the part here that I want to go ahead and consider to be f of x. And the reason why I want to do that, of course, is because if I'm going to use the squeeze theorem, I have to show that this particular function is also going to assume the same limiting value of h of x and g of x. So what we're going to assume then is that this is f of x. Now the thing that's going to happen is that we're actually going to have to build f of x. We're going to have to start off with something else. And when I take a look at this particular theorem here, this particular limit, I have x squared and I have cosine of 1 over x squared. Now the logical choice for us to choose is the cosine of 1 over x squared first. And the reason for that is because we already know that the cosine of 1 over x squared is actually going to be between two particular values of the function itself. One of which is a -1 value, and the other one, which is the 1 value. So there's our minimal value for the cosine, there's our maximum value for the cosine. So basically what's happened now is that I've just basically incorporated the f of x, which initially right now is just cosine of 1 over x squared, and I've now included the inequality sign, which are going to be absolutely essential for us to go about using the squeeze theorem. Now, again, remember what I said is we're going to have to build f of x, or in other words, we're going to have to build this function so that it looks like the f of x that we have in the squeeze theorem there. It doesn't look like that at this particular moment, but if I go ahead and multiply all three parts by x squared, then notice that what I'm going to have now is I'm going to have negative x squared is less than or equal to x squared cosine 1 over x squared less than or equal to x squared. And being that x squared is always going to be a positive value, we don't have to worry about changing the inequality signs. Now, this is now what f of x is. We just need now to go ahead and take the limit as x approaches 0. And if I'm going to take the limit as x approaches 0, this middle part of the inequality signs, I need to do it for all three parts as well. This part here and that part there. So notice that's what I've done. I've taken the limit as x approaches 0 of this, this, and that. That's still going to maintain our inequalities. And so now, of course, when I go ahead and I take the limit as x approaches 0 of negative x squared, well, of course, that's just going to be 0. And if I go ahead and take a look at the limit as x approaches 0 of x squared, that, of course, is also going to be 0. So notice what's happening now is that the only possible value that this can actually take is 0. And so we're finished with the proof that the limit as x approaches 0 of x squared cosine 1 over x squared is indeed equal to 0. Now the other thing that you all should also go ahead and take a look at, and this is one of the reasons why the squeeze theorem is so valuable as well, is that if we go ahead and just substitute the limit as x approaches 0, of course the cosine of 1 over 0, 1 over 0 is undefined. So there's no way that we can even evaluate what this particular function is, which is the reason why, except possibly c itself, comes into play as well. Okay, now in addition to actually taking a look at the squeeze theorem, there are a couple of very fundamental results that's going to come about. And these are the two special results. Okay, the limit as x approaches 0 of sine x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Both of these can be proven using the squeeze theorem. Now, we're not going to go ahead and take a look at these two particular results with this video, but of course you can go ahead and find in either your textbook or on other resources how to go about determining that these two are in fact true using the squeeze theorem. So we'll go ahead and take a look at some of these problems the next time that we meet in class. So until then, see you later.